Okay, in this video we are going to talk about the king property, or maybe it's rule or substitution or technique. I don't really know the right way to refer to it. I had never seen this before in my life, but I've recently started doing a lot of JEE practice problems or actual problems from the JEE Main exam. And this property comes up, mind-boggling. So the integral from a to b of f of x dx is equal to the integral from a to b of f of the quantity a plus b minus x dx. It's an amazing property. I'm going to show you where it comes from. And then I'm going to do like 13 or 14 examples. So maybe you do a couple examples with me and then you jump ahead and try to do them on your own. I'll have the worked out solutions in the video. It's really, really neat. Let's take a look at this. So where does this come from? Well, so what I'm going to do is I'm just going to start off with the substitution that we want to make. So what we're going to do is we're going to let x equal a plus b minus t. And then if we make this substitution, this is one of those substitutions that seemingly comes out of nowhere. Basically what you're trying to do is integrate from right to left instead of left to right. So x is equal to a plus b minus t. That means that dx is going to be negative dt. Now here's the interesting thing. If x is equal to a, so x is equal to a, then you get a is equal to a plus b minus t, negative b equals negative t, t is equal to b. So it looks like this is a substitution that's going to flip our bounds. If x is equal to b, sort of the same thing happens. We end up with t is equal to a, so you can just plug it in and see that that's going to happen. So we can rewrite our integral, just do all of our substitutions. Our bounds actually have flipped, right? So the a that was at the bottom has become a b, and the b that was at the top has become an a. So now we're going from b to a of f of, do the substitution, so a plus b minus t, and then substitute for dx and negative dt. So what happens is, because you have the integral from b to a of negative dt, you can change the sign and flip the bounds, which is a really common property. So this is going to become the integral from a to b of f of a plus b minus t dt. And this is just like spelling it differently, so we can change those t's back into x's, which will give us the integral from a to b, f of a plus b minus x, and then dx. So that's where the property comes from. Who the first genius to figure that out was, I don't know. I also can't really find the origin of the name. I'm hoping someone in the comments can just let me know if they know a little of the history of this thing. I had never seen it before in like all of the calculus books that I have. I've taught calculus for about 20 years. Never have I run into this. It's very cool. Let's look at a problem. So this is a problem that if you've done some integrals, you probably run into, and usually use the power reducing formula. But I'm going to use the king property. So what you do in almost like literally every case is you first set the integral equal to I. So I'm going to do that. Now what you do is you just say that you're going to use king property. So I'm going to say use king. In future problems, I'm going to say by king. That's mostly what people do. They just say by king. So I'm going to have I, my integral again, is equal to, so we're doing the substitution, 0 to pi over 2. So it's going to be the cosine squared of, so 0 plus pi over 2 is pi over 2 minus x. So it's going to be cosine squared. You have to do that substitution, a plus b minus x. So 0 plus pi over 2 is pi over 2 minus x, so we'll get pi over 2 minus x here, and then dx. Now, when you're doing these problems, if there's trig involved, you almost certainly are going to use some identities. In particular, you use the cofunction identities a lot. So we know that sine of x is equal to cosine of pi over 2 minus x. That is the cofunction identity. So let's make that substitution. 0 to pi over 2 sine squared of x dx. Now, here's where the magic happens on almost all of these problems. We have written this integral two different ways, right? So we have the original, and then we have what we just wrote. So 0 to pi over 2 cosine squared of x dx is actually the same as 0 to pi over 2 sine squared of x dx. So I'm going to write this out in a little more detail than I will in the future problems. So we add them together, and you get 2 times I is equal to the first integral plus the second integral that we transform using this king property. Now they have the same bounds, so you can bring them all into the same integral. And this is a very common procedure that you'll find yourself following. It's like you take the original, you take the king property, you add them together, so you basically can almost always start with just 2i is equal to and go from there. We got cosine squared plus sine squared. That is a Pythagorean identity. Sine squared plus cosine squared is 1. So really we're just integrating 1. So 2I is equal to the integral from 0 to pi over 2 of 1 dx. Well, that's just going to be, so I is going to be 1/2 of that integral. I is going to be 1/2. If we integrate that, it's just x, and then you're going from pi over 2 to 0. So that's just pi over 2 minus 0. And then that's just pi over 4. And you have the answer. And so like I spent a lot of time explaining that, but if you don't have to explain it and you know your identities, you can sail through that problem. It's pretty amazing. Let's look at another. So there's like, once you decide that you're going to learn this or you stumble across it, there's pretty much like 3 standard examples that you're going to run into over and over again. So then I like went seeking more. The next one we're going to look at is one of the standard examples. So we're going from 0 to pi over 2 of 1 over 1 plus the tangent of x to the pi. Let me tell you, in the absence of this property, I'm not entirely sure how I'd ever go about doing this integral, but it's like if you have the right tool for the job, you can unlock these sorts of things. So we're going to set it equal to I, because that's basically what we always do. We're going to say that we're using the king property to let people know that we are using this magical, amazing thing. Now, we're going to have 2I is equal to, you're going to have the original integral. So 0 to pi over 2, 1 over 1 plus tan of x to the pi. Now, we need to make the substitution. So it's going to be a plus b minus x. So 0 plus pi over 2 minus x, so pi over 2 minus x. And we take that. Every x that we see in our original integral becomes a pi over 2 minus x. So we get 1 over 1 plus the tangent of pi over 2 minus x to the pi. If you remember from the previous one, this is a cofunction identity. So cotangent is tan of pi over 2 minus x. So we'll make that substitution. So 2I is currently this thing. Now we have to do a little bit of algebra. So it's like, it makes the integrals accessible. It doesn't just do the integral for you. You still have to do some work on these. But it's usually like amazing. So I'm going to do the algebra up here. 1 over 1 plus cotan to the pi is going to be 1 over 1 plus 1 over tan to the pi. And then you get a common denominator in the denominator. So it's like tan plus 1, tan to the pi plus 1 over tan to the pi. Then you invert the fraction. We get this. So I'm going to replace 1 over 1 plus cotan to the pi with this thing, which will give us this. Now, if you look at that, you have, because they have a common denominator, you really just have 1 plus tan of x to the pi over 1 plus tan of x to the pi. So that's just 1. So this is what we're doing. This is 2 times I. So I is going to be 1/2. And again, we're just going to get x where you go from 0 to pi over 2, which is pi over 2 minus 0. I promise not every answer is pi over 4. A lot of the examples have an answer of pi over 4. I'm not sure what magically is making that happen, but like, look at that. We just blew through this integral. That integral is an integral that if I did not now know the king property, I don't think I would be able to do. I mean, if somebody knows another way of doing it, let me know. Let's take a look at another one. So this one is really close to one of the standard examples. I mean, I guess it probably is. Off the top of my head, I'm not really remembering what the standard examples are. Yeah, this is one that I would say is another standard example. Often they just fill in a value for n, but you can just do it in terms of n. So like, why do that? So here goes. Set it equal to I because that is step 1. All right, now you declare that you're using king properties. So you say by king. That's where I first discovered this. I was looking at a book that had a lot of hard, challenging problems, and I was like, I don't know what to do. I looked at the solutions, and the first step was just by king. I was like, by king? What does that even mean? So then I went on an internet search, and I found some stuff about it, and it's very neat. All right, so we're going to do the thing where we have the original integral and then our transformed integral, and we're going to add them together. So I'm just going to start with 2I is equal to, and then our original integral, so you don't have to watch that. Now, we're going to do the substitution. So it's every x becomes a plus b minus x, which is 0 plus pi over 2 minus x, pi over 2 minus x. I'm going to show it this time, and then I'm going to kind of like fade away from that and just use cofunction identities when they happen to like save a little bit of time. But here's what our second version of the integral becomes using the king property. We get sine to the n of pi over 2 minus x over sine to the n pi over 2 minus x plus cosine to the n pi over 2 minus x. you're looking at that and you're like, there's so many cofunction identities. And that's right. That'll happen all the time. So I'm just going to jump to it. The sine of pi over 2 minus x is cosine. Cosine of pi over 2 minus x is sine. So we get this. Now we want to add these together. Oh, it looks like I accidentally changed one of my n's into a 2 there, because you just see that so often. I'm not going to change it, but in that second denominator, that should be cosine to the n of x, kind of obviously. Okay, so now these have the same denominator, so you can add them. So 2i is just this. That's very obviously 1, right? So we're doing the integral from 0 to pi over 2 of 1 again, which I guess is why we keep getting pi over 4 as our answer. So 2i is equal to that, which means that I is 1/2 of that. The integral of 1 is x, and then from pi over 2 to 0 is pi over 2 minus 0. So again, we get pi over 4. And like I said, it's not always going to be pi over 4, but I guess that if you're doing this type of integral and you just have to guess, like pi over 4 might be a good guess. I don't know why you would have to guess, though. All right, let's do another one. We're doing a lot. So, you can, at this point, if you think you've got it, like just look at the problem, try to do it, and then maybe look at the solution, or you can keep watching. I'm going to do them in as much detail as I think is necessary. All right, all of these are king property. We set it equal to I. Now, we declare that we're using king property. We're going to add our two versions of the integral together. So we're going to have 2i is the original plus, use the king property, but this time it's 0 plus pi over 2 minus x. So that's pi over 2 minus x. It's all cofunctions, so I'm just going to do it, right? Our sine becomes cosine, our cosine becomes sine. So we have this. And then this is like a slightly more complicated problem than the last one. We're going to add these together. We have a sum of cubes in the numerator, and so now we need to remember how to factor a sum of cubes. So sum of cubes, if you have a cubed plus b cubed is a plus b, quantity a squared minus ab plus b squared. I remember that by using SOAP for the signs, right? So it's a plus, minus, and plus. So SOAP, so it's the same sign. So it was plus in the sum of cubes. It's plus for a plus b. And then it's the opposite sign, so it's minus AB, and then it's always a plus at the end. Okay, so we got to factor this, so let's do that. I don't think you have to watch this. It's going to be sine plus cosine, and then sine squared minus sine cosine plus cosine squared, all over sine plus cosine. The sine plus cosines cancel, so this is getting a lot simpler. But now we have sine squared plus cosine squared, which we know is 1. So I'm going to combine those into 1. So our integral simplifies to 2i equals 0 to pi over 2, quantity 1 minus sine cosine. I never know how much to show and how quickly or slowly to go on these, because I mean, if you're up to these types of integrals, I'm assuming you can also do substitutions and simplifications. But I also want to fill in the blanks for, I know that I've done a lot of problems where I've eventually had to kind of give up and look at the answer, and I'm like, this doesn't make any sense either. So I'm trying to make it so that, I don't want that to happen to you. That's why I'm showing a lot of steps. All right, we got to integrate this thing. The sine x, cosine x, I think the easiest way to deal with is to use the double angle formula for sine. So sine of 2x is 2 sine cosine. So what I'm going to do is I'm going to replace sine cosine with 1/2 sine of 2x. So that'll change my integral to, instead of 2i, I'm just doing I is 1/2 of 0 to pi over 2. The 1 stays, we replace sine cosine with 1/2 sine of 2x. And then we can integrate from there. So it's 1/2 quantity x. And then you're going to get a, so it's, you end up with negative 1/2 times negative 1/2 cosine, so plus 1/4 cosine of 2x. And then from 0 to pi over 2. All right, so we're going to sub in. When we sub in for pi, we get obviously pi over 2. And then you get 1/4 the cosine of pi, which is negative 1. And then minus, let's do a quantity, plug in 0. Don't forget the cosine of 0 is 1. I see that people get really happy when they see oh, I'm just subbing in 0. But not everything evaluates to 0 at 0, right? In particular, cosine and e to the x evaluate to 1. And it is the source of so many errors. If we clean this up, we get 1/2 quantity pi over 2 minus 1/2, which is pi minus 1 all over 4. So finally, we didn't just get pi over 4, but we still got a pi over 4. It's not always going to happen. All right, let's try another. So like I said, I'm just doing a lot of examples here, but I think it's so cool and amazing, and it like gives you the chance to do integrals that you would maybe not be able to handle otherwise. All right, so we're going to use a king property, so I'm going to say by king. I'm going to do the thing where the original integral and my transformed integral, I'm going to add together, so I'm going to have 2I is the original integral. Now I'm going to just, again, if I do a plus b minus x, I get 0 plus pi over 2 minus x. Pi over 2 minus x, I'm just going to use the cofunctions. All my sines become cosines, all my cosines become sines. So I get cosine x minus sine x over 1 plus cosine times sine, because every cosine became a sine. All right, if we look at this is pretty interesting. 2I is 0 to pi over 2. So, I mean, look at the numerator. You have a cosine, a negative cosine and a cosine, that's 0. You have a sine and a negative sine, that's 0. We're just integrating 0. So this problem is just 0, and you basically don't need to do anything. In the absence of the king property, I don't know what you're doing, right? Like, I mean, this one looks like you could work it out in the absence of that, but I'm not sure where I would begin. I didn't try to tackle these in other ways. I was just like, this is the way. All right, let's look at the next one. 0 to pi of x sine of x over 1 plus cosine squared of x. All right, we're doing it. I'm going to set it equal to I. We're going to declare that we're using the king property. And again, we're going to add the two integrals together. So we're going to have 2I. So you don't 100% of the time add the two integrals together. But from the examples that I found, you like, I don't know, 13 out of 14 times do. So I guess it's just experimentation. Like you look at the transformed integral and you think, can I deal with that? If yes, do it. If not, then you're going to end up adding them. All right. So it's 0 plus pi minus x. So pi minus x. This is not a cofunction situation. Every x becomes a pi minus x. So we're going to have pi minus x sine of pi minus x over 1 plus the quantity, I guess, cosine of pi minus x squared. Okay, so we still need to know some identities here to work this out. So first of all, the sine of pi minus x is exactly the same as sine. You can use the difference formula for sine if you're not really sure, but I assure you that is true. And for cosine, cosine of pi minus x is the negative of cosine of x, which again, if you want to confirm that, use the difference formula. Okay, so let's rewrite this thing using those substitutions. So we get the original integral, pi minus x, our sine of pi minus x becomes sine of x, 1 over, now we have the quantity negative cosine squared, but negative cosine squared is just cosine squared again. So that's why I paused there to make sure I could explain that part. All right, they have the same denominator, so we're going to be able to write them as one fraction. If you look at this, there's some distributing you can do here in this second numerator. So it's going to be, you have pi times sine, and you also have negative x times sine. So you have x sine x plus pi sine x minus x sine x. The x sine x's just cancel out, which is magical. So all that's left is pi times sine of x in the numerator, and the denominator is obviously still there. All right, so this, if you look at it, I mean, you can take out the pi, and you can say, like, the integral itself is going to be pi over 2, and then we have to, like, work out what's happening. You have sine over 1 plus cosine squared. That's definitely arctan. I'm going to do the u-substitution just to, like, make it really clear, but that's definitely arctan. So if we let u equal cosine, then negative du is sine of x dx. When x is pi, we get u is negative 1. When x is 0, we get u is equal to 1. Okay, so we can fill in the blanks, right? We get negative pi over 2, integral from 1 to negative 1 of 1 over 1 plus u squared, which I would choose to change the sign and flip the bounds, because that's just what I like to do. All right, this is a perfect arctan. So we're going to get pi over 2 arctan of u from negative 1 to 1, which is pi over 2 arctan of 1 minus arctan of negative 1. The arctan of 1 is pi over 4, and the arctan of negative 1 is negative pi over 4, so we have pi over 4 plus, well, we have pi over 4 minus negative, which is plus. Pi over 4 plus pi over 4 is pi over 2, so really we have pi over 2 times pi over 2, so our answer here is going to be pi squared over 4, which is kind of amazing, but again, king property, killing it. All right, let's take a look at another This one feels the same to me. Like, it feels like basically the same problem, except, you know, in the previous one, there was just an x in the numerator, and this looks more complicated because we have x squared, and then we have a quantity 2x minus pi in the denominator. We're still just going to use king property. Here we go. So by king property, we're going to do the thing original, and we're going to get the transformed, we're going to add them together. So I'm going to say 2i is equal to the original plus, it's 0 plus pi minus x. So that's pi minus x is our substitution. So pi minus x squared, sine of pi minus x, which we know is the sine of x, over. Now here we have to like work this out. So we're going to have 2 times the quantity pi minus x minus pi. This is just like, you know, basic algebra, but you still have to do it to make sure you're getting it right. This, so that's going to be pi minus 2x, which inevitably we're going to have to deal with because now we have a 2x minus pi and we have a pi minus 2x. So yeah, we're going to take out a negative at some point. And then we get this 1 plus the cosine squared of pi minus x. All right, so we know a couple of things here. Let's jump. Our numerator is going to be, because we already know, well, our denominator, I guess, is what we have to deal with. Pi minus 2x is just the negative of 2x minus pi, so let's pull that negative out. And then also we know the cosine of pi minus x is the negative cosine of x. And let's just jump this. We know the sine also. Just filling in the blanks, right, in case people aren't sure. So here's what we get. Minus the quantity pi minus x squared times sine over 2x minus pi quantity 1 plus cosine squared. That's where we stand now. They have the same denominator, so we can like combine. I'm going to factor a sine out of everything in the numerator. So sine comes out, and we get x squared minus the quantity pi minus x squared. How are we dealing with this? We're going to expand that x squared minus quantity pi minus x squared. I'm going to do it like up on the top here. So just expand, collect, factor out of pi. So we have pi times the quantity 2x minus pi is times sine of x. That's our numerator. So pi quantity 2x minus pi sine of x over 2x minus pi times 1 plus cosine squared. It's easy to forget like that there's so much else in this problem. So the 2x minus pi's cancel. We can factor out the pi, and that's 2 times the integral, which means the integral is going to be pi over 2. And then we just have sine of x over 1 plus cosine squared of x. This is literally the last problem that we did, right? Like we just got the exact same problem. We did all the substitution, all that work. This is exactly the same problem we did before. So we know the answer is pi squared over 4. That's insane. I mean, that's the kind of thing that happens when you dive into these sorts of problems. All right, the next one is going to be another standard example. If you look this up on the internet, you will see this problem done every single time, I think. I'm not sure why this is the standard example, but it is. This one's a little annoying because we do want to use the king property, but you have to do something else first. You have to kind of transform, like, so you see x squared plus 1 in the denominator. That's sort of suggestive of arctangent. So I'm going to let x equal tan of theta. This is like an entirely different type of substitution, kind of a trig substitution. So x is tan of theta, which means dx is secant squared of theta d theta. If x is equal to 1, that means that theta is going to be the inverse tangent of 1, which is pi over 4. If x is equal to 0, theta is going to be the inverse tangent of 0, which is 0. So before really doing the king property, I'm going to transform this thing into an integral in terms of theta. So let's do that. Do every substitution. We get our integral I is 0 to pi over 4, natural log of tan of theta plus 1 over tan squared theta plus 1, and then dx is secant squared of theta d theta. So that's what we have. Now what do we do with this? Because this looks gross. One thing that we definitely know is that 1 plus tan squared is equal to secant squared. That's one of the Pythagorean identities, which means that 1 plus tan squared in the denominator here and the secant squared of theta are the same and they cancel to 1. So I'm going to do that. That brings us to this. 0 to pi over 4, natural log of tan of theta plus 1. Okay, so now I'm going to do the king property. So here goes. I'm going to get that. So I'm not going to double it this time, though. And this is like trial and error, perhaps, where you find out that you don't have to double it. It could just be that when you use the king property, it's not really suggestive that doubling is going to help you at all, and that's maybe why you don't do it here. So I'm not doubling, I'm just applying the property, right? So it's 0 plus pi over 4 minus theta, I guess, in this case. So that's pi over 4 minus theta. Every theta becomes pi over 4 minus theta. So our integral is 0 to pi over 4, natural log of the quantity pi over 4, or tangent, the quantity pi over 4 minus theta, and then plus 1 d theta. All right, so where do we go from here? Well, I'm going to use the difference formula for tangent, right? So the difference formula for tangent is going to be tangent of pi over 4 minus tangent of theta over 1 plus tangent of pi over 4 tangent of theta. Tangent of pi over 4 is 1, though, which kind of like is fantastic in this case. So we get 1 minus tan of theta over 1 plus tan of theta. So we can change the tangent of pi over 4 minus theta into that, so that's what I'm going to do. So I will end up with my integral is 0 to pi over 4, natural log of the quantity 1 minus tan of theta over 1 plus tan of theta, plus 1 d theta. Okay, so if I get a common denominator, I will have 1 minus tan theta over 1 plus tan theta, plus 1 plus tan theta over 1 plus tan theta, right? So they have the same denominator, so the numerator is 1 minus tan theta, plus 1 plus tan theta. So 1 plus 1 is 2, negative tan theta plus tan theta is 0. So really we just have 2 over 1 plus tan theta. So that's going to be our new version of the integral, which we're going to put up here. So this becomes 2 over 1 plus tan theta. What we did there was we got a common denominator. We just combined everything that's inside the natural log. That's where that came from. Looks a little magical. It's not. If you have division within natural logs, it becomes subtraction between them. So our integral, 0 to pi over 4, natural log of 2 minus the natural log of 1 plus tan theta. Okay, so now what I'm going to do to make it a little clearer how this is working is I'm going to rewrite this as two separate integrals. So we have the integral from 0 to pi over 4 natural log of 2 minus the integral from 0 to pi over 4 natural log of 1 plus tan theta. Now you might recall that is the original integral. You also might not have recalled that because it's been a while since you thought of it. So if we do the actual integral on that, we just get pi over 4 natural log of 2. This guy is the same as this guy, which means we can just make it I again. Which means we're kind of back where we were, where we are getting 2i, but we get it in a different way. At least I'm thinking that we get it in a different way. Maybe if you're watching this, you see oh, you're doing the same thing. I don't know. Feels different. Divide by 2. This integral is pi over 8 natural log of 2. Would we get it without the king property? I don't know. It feels like an integration by parts problem, maybe, in the event that you're trying to do it that way, right? Because you can take the derivative of natural log of x plus 1. You can integrate 1 over x squared plus 1. Feels like an integration by parts, but I didn't try it. That would be my attempt if I were not using the king property. All right, next problem. 0 to pi, 1 over 1 plus tan of 1 over 1 plus 2 to the tan of x. There we go. All right, this is straight king property. That's I. We're using the king property, so we're going to add them together again. So we get 2i is our original integral plus 0 plus pi minus x. So pi minus x. So 1 over 1 plus 2 tangent of pi minus x. We obviously, there's something going on between tan of pi minus x and tangent, right? So you can use the difference formula if you want. Tan of pi minus x is the negative of the tan of x, which I'm sure if you're studying for JEE, you have memorized so many formulas, and that is definitely on the list. So we're going to replace tan of pi minus x with negative tan of x. So we get this. This problem is basically the same as one of the first couple that we did, where now we're just going to rewrite that second part of the integral, the second fraction there, using just positive exponents. So it's 2 to the negative tan x becomes 1 over 2 to the tan of x, common denominator, invert the fraction. So we're going to get 2i is 0 to pi, and then our original 1 plus 2 to the tan of x, and then this will become 2 to the tan of x. That's so hard for me to say for some reason. 2 to the 10 of x plus 1. Add them together, magically, you get 1 plus 2 to the 10 of x over 1 plus 2 to the 10 of x. You just get 1. So 2I is equal to the integral from 0 to pi of 1. The integral from 0 to pi of 1 is just pi. So that means that our integral is just pi over 2. And it just like drops out. It's amazing. I can't tell you how amazed I am. Like I couldn't summarize how amazed I am by this property. It's great. How did I never learn this? All right, new problem. And this one looks substantially different because there's no trig in it. But that doesn't mean you can't use the king property, and this thing just kind of like melts when you use the king property. So let's look at it. This is going to be I. We're going to use king property, and we're going to add both of the versions of the integral. So we're going to go 2I is our original integral plus, so it's 6 plus, well, it's a plus b, 3 plus 6 minus x, which is 9 minus x. Every x becomes 9 minus x. So it'll be the square root of 9 minus x over square root of 9 minus x. Then you have square root of 9 minus the quantity 9 minus x, which is just the square root of x dx. You look at that and you're like, that's root x plus root 9 minus x over root x plus root 9 minus, it's just 1 again. So 2I is equal to the integral from 3 to 6 of 1. The integral from 3 to 6 of 1 is 6 minus 3, which is 3. So this integral is just 3 halves. Can't even imagine doing this without that. I mean, I guess I would do a substitution. Maybe I'd rationalize the denominator. I don't know. You know, it's like once you see the light of using the king property or procedure or rule or substitution, it's how you want to do all the problems. So it doesn't work on every problem, or it's not necessary on every problem, that's for sure. But man, is it useful when it does work. All right, let's look at this one. This looks basically the same, and I bet it's basically the same, and that's why you do practice problems. So I'm going to say we're going to add the two integrals together, so we get 2I is the original. We're going to do 2 plus 3 minus x is 5 minus x. So like in terms of the structure, you'll often see a plus b minus x like within the integral, which has got a trigger in your mind, like maybe I should be using the king property on this. But again, you have to like get to the point where you're seeing that. So 2 plus 3 is 5 minus x, so every x becomes 5 minus x, and you can probably already see how this is going to play out. We get this, and then 5 minus the quantity 5 minus x is just x again. So we have this. Again, when you add those together, you get 1. So 2I is going to be the integral from 2 to 3 of 1. And the integral of 1 from 2 to 3 is just 3 minus 2. So we get 1 half. Well, I is 1 half of 3 minus 2. So 1 half. It's amazing. All right, now, the next problem we're going to look at is one that, like, without the king property, I don't know what I would even begin to do with this problem. And honestly, until I start doing problems for JEE practice, like the greatest integer function just never came up. It does not come up very often, if at all. And like the types of problems that I do and that I teach, it is heavily emphasized on all of the practice problems that I've been doing for this. So it's an important function in this, part of the math world, I guess. We're going to call it I. We're going to do the same thing, and it's going to really help us out. So 2I is our original integral. 4 plus 10 is 14 minus x. So every x becomes 14 minus x. So we're going to get the greatest integer of quantity 14 minus x squared. 14 minus the quantity 14 minus x is just x. So we're going to get greatest integer of x squared, or greatest integer of x squared, rather, and then every x becomes 14 minus x. This perfectly, again, 2I integral from, 2I is the integral from 4 to 10 of 1, so I is just 1 half of that. The integral from 4 to 10 is 10 minus 4, which is 6, so this is going to be 1 half of 10 minus 4, 1 half of 6, which is 3. Never in a million years would I have gotten this if I was not aware of king property, but it's the right way to do the problem. So once you know that, that's not like, not knowing a method. Am I just justifying this for myself? Maybe. But not knowing that something exists, you're not at fault for not being able to do the problem. Like, I never would have been able to do the problem. Now that I know this exists, like, yeah, I can do the problem, and it's like a fast problem. All right, next up, I got two more. So negative pi to 3 pi, natural log of secant minus tan. We're doing it. We're doing the king property. So we're going to say by king. We're going to add our integrals together. So it's going to be 2i is the original. All right, so 3 pi. Oh, I did this wrong. 3 pi. I did this wrong, but in a non-fatal way. I accidentally did b minus a minus x, which gives me 4 pi. I should actually have done negative pi plus 3 pi is 2 pi minus x. So I'm going to fix that because I think I only have to fix it in one place. So let's see. I'm going to let this run, and as it runs, I will try to, that should be a 2 pi. Maybe I'll just talk my way through it. This should be a 2 pi. And what's really convenient about how I screwed this problem up is that what is true for 4 pi minus x is also true for 2 pi minus x, so I've done the problem wrong. I hope I didn't do the next one wrong too. No, I didn't, but I actually tried to. I'll explain that when I get to it. I was supposed to add them. I should have had 2 pi. That's okay though, because I'm going to use some properties here. And since the period of secant is 2 pi, anything that happens for 2 pi will also happen for 4 pi. So the secant of 2 pi minus x is the same as the secant of negative x, which is just the secant of x, because secant is an even function. It should have been a 2 pi though. I'm not going to fix it. I'm just going to talk my way through it. And probably, if this video catches on, 1,000 people will tell me that it should have been 2 pi, because people don't listen, they just scroll through. Okay, and then the next one will be tangent with the same issue. The tangent of 4 pi x, so the period of tangent is pi. So whatever happens for pi will also happen for 4 pi, will also happen for 2 pi. So tan of 4 pi minus x is the same as the tan of negative x. Tangent is odd, so that's the negative tan of x. Okay, so that's the mistake. It's going to disappear at this point, hopefully. So my secant of 4 pi minus x, which should be 2 pi minus x, is just going to become secant of x. My tangent of 4 pi minus x becomes negative tan of x. So that's secant minus negative tan is secant plus tan. So we have this. All right, when you are adding in between natural logs, you should multiply the things. So this is going to be 2i is the natural log of secant minus tan times secant plus tan. And that is going to give us, so I'm going to show, I always have my students memorize that this is just 1, but you may not have that memorized. I feel like if you're preparing for this exam, you probably do have this memorized, but so 2i is going to be the natural log, the integral from negative pi to 3 pi, natural log of secant squared minus tan squared. So we know that 1 plus tan squared is secant squared, so secant squared minus tan squared is 1. So this is the natural log of 1. Is it disappointing when you do these problems and get 0? I don't really think so. I think it's actually kind of nice, right? Natural log of 1 is 0, so we're just integrating 0, which just gives us 0. So little mistake there on the 4 pi. All my 4 pi's in this problem should have been 2 pi's. I apologize, but this is a lot of writing, and I'm the only one who checks it. So that's where if you've made a mistake and you, in your mind, just believe it is correct, it doesn't really matter how many times you check your work. You're just going to keep making the same mistake again. And that's what happened to me here. What's interesting is on this problem, I tried to do this again, right? I tried to make the same mistake. I tried to do basically b minus a minus x. That is not the king property. King property is a plus b minus x, which means it's pi over 8 plus 3 pi over 8, and then minus x. Pi over 8 plus 3 pi over 8 is 4 pi over 8, which is pi over 2 minus x. So we're doing the king property. We're going to do it right, hopefully. So by king, we're going to add these two things together, the original, and then, so because 3 pi over 8 plus pi over 8, on a psychological level, I'm really interested in what happened to me on the last problem, because then I tried to do it on this problem, but then I had so here's what I did. I did 3 pi over 8 minus pi over 8 is 2 pi over 8, which is pi over 4. And I just ended up with this gross thing where I'm using sum and difference formulas, and it's not looking like it's going to work out. And it shouldn't have worked out because it wasn't right. But instead, where every x becomes a pi over 2 minus x, which means all of our sines are going to become cosines, and cosines are going to become sines by the cofunction identities. Let us do that. Natural log of quantity 4 plus 3 cosine over 4 plus 3 sine. Okay, Addition between natural logs becomes multiplication within the natural logs. So we get this. But this, again, just gives us the natural log of 1, which is 0. So it simplifies to this. You're just integrating 0, which is 0. It doesn't matter if you take 1/2. This integral is also 0. And that's it. That's like a bunch of example problems. If you've never seen this before, it is awesome. Be on the lookout for it, especially as the problems get way more challenging. It seems to be like the key to unlocking a lot of problems. Like, I'm not sure how you're doing them otherwise. But I thought it was amazing. I wanted to share it. I hope this was helpful, and good luck.